Hi guys, I hope you're doing well. On my side, everything is still fine. So in this video, we're going to discuss what we call study unit 4, which is called Systems of ODEs. Study unit 4 is called Systems of ODEs. I have already mentioned from the previous videos that we have several methods that we can usually use to solve system of ODEs, but in our case we are only limited to use Laplace transform. This is the first method that you can use to solve systems of ODE. We have the Laplace transform, and the second method which we are limited to use, the second method which is prescribed for us to use, is what we call the eigenvalues and eigenvector. I have explained or made some videos which actually explain this part of the Laplace transform. So in this video I will be explaining the theory behind eigenvalues and eigenvectors, how to solve systems of ODE, provided you have eigenvalues and eigenvectors. So if we come here, if we try to look at this part here, it says eigenvalue. Eigenvalues are divided into three. We have the first one, the second one, and the third one. What do I mean by eigenvalues are divided into three? When I say eigenvalues are divided into three, I'm only referring to the nature of the roots. I'm only referring to the nature of the roots. So the first nature of the root that I believe everyone is familiar with is real distinct roots. And then we have the second roots, which is real repeating roots, and the last one is what we call complex roots. What exactly is real distinct root? Real distinct root, let's say maybe we had to solve for lambda. It means that we have lambda 1 which is equals to something, and lambda 2 which is equals to something. We say the roots are real and distinct. The word distinct only refers to, it means different roots. So real distinct root, it means real different roots. For example, lambda 1 can be equals to 1 and lambda 2 can be equals to what? To 5. So we say the roots are real and distinct. Okay, let's move to point number 2, when we have the nature of the roots which are real and repeating roots. What do I mean by real and repeating roots? For example, let's say we have lambda 1 which is equals to lambda 2 which is equals to something. In this case, let's say it's equals to 7. For example, let's say you were solving for x and then end up with x minus 2 squared is equals to 0. You can see that the roots for this guy are the same. We're going to have x is equals to 2 or x is equals to 2. We say these roots are real and repeating because we have x1 which is 2 and x2 which is 2 here. We say the roots are real and repeating. That's why here you can see we have lambda 1 which is equals to lambda 2, and in our case we made an example with 7. So what do we mean by complex roots? Let's move to the last one, which is the nature of our roots is being complex. When you talk about complex root, the complex root are denoted by lambda, which is equals to alpha plus minus j beta. So one might actually ask yourself, well, what is this lambda and what is this beta? Lambda is the real part, of the complex root, and beta is the imaginary part. is the imaginary part of the complex roots. So if you are trying to solve your differential equation, for example, this is square root of -4, it's going to give you complex roots. We say the roots are complex because we have the real part and the imaginary part. So basically, in short, we have three types of roots: the real distinct roots, the real repeating roots, and the complex root. And the most important thing is that all those basics that we have been doing, calculating the eigenvalues and calculating the eigenvector, they're still going to apply when you're solving systems of ODE using eigenvalues and eigenvectors. So now I want us to talk about the solution. Let's talk about the solution. Number one, let's talk about the solution of real distinct root. Let's talk about the solution of real distinct root. Well, the solution of real distinct root is given by x is equals to c1 k1 e to the exponent lambda 1 t plus c2 k2 e to the exponent lambda 2 t plus c3 k3 e to the exponent lambda 3 t. This is the solution. This is the solution for real distinct root. When you solve your systems of ODE, and by any chances after getting your eigenvalues, you realize that you have 3 eigenvalues, it means that the solution will be this guy here. It will be given by x is equals to c1 k1 e to the exponent lambda 1t plus c2 k2 e to the exponent lambda 2t plus c3 k3 e to the exponent lambda 3 t. Okay, as you can see, I have written when we have this guy, the solution, this is the solution for real distinct root. Why am I saying this is the solution for real distinct root? Because you can see here we have lambda 1, we have lambda 2, we have lambda 3, meaning we have lambda 1 which is equal to something, we have lambda 2 which is equal to something, we have lambda 3 which is equal to something. You can see what these guys, we have our real distinct roots. This is exactly what I was explaining here. Lambda 1 is equals to 1, lambda 2 is equals to 5. So you might ask yourself, what exactly is K1, K2, and K3? So in short, K1, K2, and K3 are our eigenvector respect to lambda 1, lambda 2, lambda 3. So K1 goes with lambda 1, K2 goes with lambda 2, and then K3 goes with lambda 3. So basically, in general, if you are required to determine general solution, you're going to use this equation. You just need to get the eigenvector for this guy, and then the eigenvalue you substitute here, and then this will be your answer. Okay, let's move to our second nature of roots, which we have discussed from the previous, which is real repeating roots. Real repeating roots. Okay, when we're dealing with real repeating roots, I have already mentioned that lambda 1 is equals to lambda 2, which is equals to something. Let me just call it alpha in this case. Ne? So under this real repeating roots, the general solution equation, the general solution is given by x, which is equals to c1 small x1 plus c2 small x2, and this x1 is equals to k1 and then e to the exponent lambda t, and x2 is equals to e to the exponent lambda t into what? K1 multiplied by t plus k2. So to explain this, when you have real repeating roots, which means lambda 1 is equals to lambda 2 and they are all equals to alpha. The general equation is given by this guy here, which is x is equals to c1 x1 plus c2 x2, whereby x1, this x1 here, is equals to k1 e the exponent lambda t, and this k1 is what we call the first vector, and then the k2 here is what we call the second vector. So it is crucial, it is very important for you to first get the eigenvalue and then get the eigenvector. After getting the eigenvalue and the eigenvector, you just substitute into x1 and then x2, and then you take it back to the original equation, and then you are actually good to go. So this conclude the general solution of the real repeating roots. So now we're actually moving to the last part, which is complex root. Complex root, as I have already explained, that complex root is divided into two parts, which is the real plus minus j beta is the real and the imaginary part. This is the real part and this is the imaginary part. So what is the general solution? The general solution is given by this formula, which is x is equals to c1 x1 plus c2 x2. But in this case, since we have complex root, our x1 is not going to be the same as this x1 here. This is only for real repeating roots. So since we have complex root, our x1 is going to be equal to e the exponent lambda t into c cos of beta t minus d sine of beta t, and then this x2 here will be equal to e lambda t. The sign fluctuate and then the d becomes the c, and have d cos of beta t plus c sine of beta t. So this x1 is equals to this whole guy here, and the x2 is equals to everything here, and then you're going to substitute it back inside the original equation, and then this is how you actually get the general solution. Note that for c1 and c2 we call this constant. C1 and c2 we call them constant. So our constant we get them using the IVP. What do I mean by the IVP? The IVP, I'm actually referring to the condition that you will be given. So if you are not given the condition, you cannot get the value of C1 and C2. But if you are given the condition, and then it is simple for you to get the value of C1 and C2. So we're going to call this C1 and C2 our constant. Even here, C1 and C2, this is our constant. So once you can grasp this part that we have three types of roots, which is real and distinct root. We have real distinct root, real repeating roots, complex root, and this is the general solution for real distinct root. Note that if you are working with a 2 by 2 matrix, you're going to have C1 and C2. The reason I added C3 is because we are working with 3 by 3 matrices. So if you are working with 2 by 2, you can stop here. 3 by 3, you add this guy here. And then real repeating roots, general solution is given by x is equals to c1 x1 plus c2 x2, and then you know that x1 is given by this guy, x2 is given by this guy, and then you substitute back. And then for complex roots, you know that complex roots have the real part and the imaginary part. The general solution is given by x1 is equals to c1 x1 plus c2 x2, and then x1 is given by this guy here, and then x2 is given by this guy, and then you substitute back into the original equation. So this is